Moving on to a new chapter, chapter 8. We're skipping 8.1, but we'll come back to that. But chapter 8 is about displacement. You all know displacement to be something moves. So we have the more complicated technical definition here, which is a vector representing change in position of a body or a point with respect to a reference. It moves. Want to measure that? Why do we want to measure that? There are endless applications. I have a few here. So all of these are in the category of manufacturing quality control. Here we have a go, no-go gauging. If this manufactured part, you measure to see if it fits within the tolerances, and if it does, it goes. If it doesn't, it's a no-go. Here, like rolling out some sheet metal, and they're monitoring the thickness of it. Here, they're checking the contour of an airplane, so multi-point, more than one dimension, three-dimensional. Structural testing, again, we have an airplane here so they've loaded up the wings and checking, they're measuring underneath like what we see here to see how much those wings are displacing from that load. Here we have some stone next to some modern steel structure. I don't exactly know the context here, but I've seen some places where there are old ancient buildings that have been reinforced or have modern buildings built right next to them. That might be what this is. They're just checking that old stone structure to make sure it's not moving around. Here, kind of doing something similar, but looks like a bridge maybe. Balancing operations. Here you have an automotive crankshaft. So they're just they're measuring the displacement of that crankshaft to make sure it's balanced. Robotics, that's a big application. So AC servo motor, you see all these different axes of motion. Each one of those, servo motors not only move it, but then they have an encoder in them that they give feedback as to, like, I'm at this location or I'm at this location. So you get a measurement out of it also. Helps you to control the location. We don't cover that a whole lot, but the book has a little section on how those rotary encoders work. That's part of your reading assignment. Have some videos here about some robotic stuff. You've probably seen a lot of these, but they're still fun to watch. another one of theirs. Boston Dynamics. I was recently, just like a couple, like 2 months ago, at the Boston Dynamics headquarters, and they have like a museum in the lobby. I took a couple pictures of some, like this is a kind of like a preliminary version of that Atlas one. So it's pretty amazing how much it changed in a pretty short period of time. And they also had this other one that I haven't seen a video for before, but it's climbs up walls. Some little, interesting little bug-like thing. Anyways, back to this. That's the Atlas. So that's the newer version of that first picture I showed you. This is BatBot. So we have 40 plus joints for flight, most sophisticated powered flight mechanism among animals, and they've made a robot that it's not perfectly, but it's getting pretty close to simulating it. Okay, this is CatBot. I've mostly just put this in here as a bad joke. Somebody loved their cat and decided to turn it into a CatBot or a quadcopter instead of burying it. And then I have another bad joke here. This isn't brain surgery. Actually, it is. So displacement of the probe. So here's a probe used in brain surgery. So displacement of this probe is accurately measured while it carefully places electrodes in the target area of the brain. And then way back, probably on the first day, we talked about displacement being a base unit and then there being all these other derived units. So besides just measuring displacement to get the displacement, which we saw there's endless applications for, we also, if we measure displacement, then we can get all these other derived units like this list here. So force, stress, pressure, velocity, acceleration, etc. Here we have an example of that. So it's a pill making machine. Just pointing out a couple things that it measures. Pill thickness is the first one, and this is just displacement, right? We're measuring the thickness of the pill. So displacement of roller pressing medicinal powder into pills is precisely monitored to ensure desired pill thickness. That's just the base. But the derived unit, here we have force. So to get the pill weight, right? Weight is a force. So we measure the displacement of a slider ramp that holds the medicinal powder that is monitored to control the amount of powder and eventually the weight. Another good application of measuring displacement is we can take old analog devices and turn them into modern devices that can work with our DACs. So here they're using a Bourdon tube. Do I have a picture? No, we don't. Let's. Probably a lot of you know what a Bourdon tube is, but let's just see one. Let's see if I can find an actual picture of one. Here, this is what the inside of them actually looks like. So you connect this up to whatever pressure you're trying to measure. And if the pressure increases, then this tube up here that pressure fills will expand out this way. And if it decreases, it'll contract this way. And now let's see one of those schematics. If maybe like this one, or no, this one's better. So as that tube moves out or in based on the changes in the pressure, there's this mechanical linkage, and it looks like there's a torsional spring here, and it moves this needle on a dial. So, but you know, this been around for many years. It's a useful device, but you have to go and look at the gauge to actually see what the pressure is. Instead, say we have the measurement coming into this board-on tube. If we instead put something on there that measured the displacement, like say we put a strain gauge on there, then we can get, if we put that strain gauge into Wheatstone bridge, we can get a voltage out that we can calibrate, so our DAC will get us, dynamic data that we can we can monitor remotely, or we can do some post-analysis to it. So all those benefits of a modern DAC system. Okay, how do we measure displacement? The first thing that we're going to study is using a potentiometer. And basically it's a variable voltage divider. Right, we already covered the voltage divider with the Wheatstone bridge. You have your source voltage, and then there's this one long resistor, but we have a slider on there that divides it into two different parts. So it's like you have your R1 and R2, and the ratio between those is going to be dependent on the position of your slider. So the output voltage is going to be dependent on that. So variable resistor, resistance varies as a function of slider position and wire wrappings. We'll talk more about those wire wrappings here pretty soon. Like we said, essentially it's a variable voltage divider. So this equation we use is this one here in the red box. The output voltage is the ratio of the slider position divided by the total length times the source voltage. It's pretty simple how it works. You apply a known voltage, you measure the output voltage, just the voltage drop across this resistor. And then the voltage is proportional to the distance the slider has moved along the winding. You do need a high input impedance for this, and that complicates it. We'll do at least one example today that shows how to do that. Here are some potentiometers that are used to measure. So this is the linear type. And then you can also use potentiometers to control. Here's a slider on a control board. There are also angular potentiometers, and the core concept is the same thing. It's just angular instead of linear. So you still have an output voltage that is proportional to the angular displacement. So you have angular displacement divided by the max angular displacement. And here I'm showing just this as the max, but it can be designed so that there are multiple rotations. It's easier to comprehend it visually in 2 dimensions like this. So you just multiply that times that source voltage, and that's your output voltage. Oh, here I have this note, can be designed for multiple rotations. Here are angular potentiometers that are used for measuring. And here are angular potentiometers used for control. Another video for you.
What we do is we need that extra push up and everything. You know what we do? Yeah, exactly. Why don't you just make 10 motor and make 10 with the top number and make that with the these not do that.
This lecture is full of bad jokes today. That's from Spinal Tap. If you haven't watched that and you kind of like old British humor, it's pretty hilarious. At least I thought it was when I watched it long ago. You might have to have a weird sense of humor. Okay, back to serious stuff. We have the capabilities, advantages, and disadvantages of potentiometers on this slide. So for capabilities, first one is linear, can measure displacements from 0.1 inches to greater than 1 foot. And angular can measure displacements of 3,500 degrees, so almost 10 rotations. And you can design them to have nonlinear relationships, but most of them are linear. The advantages are they are inexpensive and simple. There's no signal conditioning required. You just apply an input voltage and you get an output voltage depending on the displacement. And then disadvantages are you have a finite working life. Most of you probably have experience with this. If I guess nowadays it's mostly touch screen stuff, but anything that has a knob on it probably has is probably a potentiometer. And you've probably, like if you have an old stereo or something like that and you turned it and you hear that little crackling noise, you're hearing it degrade, getting corroded, moving towards the end of its life. We already mentioned that need high input impedance. That kind of complicates the output. It complicates the analysis and the output. We'll cover that more here soon. They don't have great resolution. It's very expensive to get resolution that's less than 0.05 inches. And we're going to demonstrate why that is also here soon. Then kind of maybe going back to this first point in the disadvantages, it produces significant noise due to contact surface contamination. So potentiometer, now the part about potentiometer resolution, like why it's hard to get less than 0.05 inches. Most of these are constructed by tightly winding a fine wire around an insulating form. So that's what we see here. We have this insulating form underneath, and then you see these wire wrappings around it. And here's the slider that moves over it. What you get out of that is, here's your slider. So your slider is going to move from wrapping to wrapping to wrapping. So it's going to be a stepwise output, right? Basically every wrapping around there is going to be how much you can move. So you can't, it's not a continuous thing, it's discrete. You jump from wrapping to wrapping to wrapping. So resistance changes in discrete steps. The best potentiometers use 2,000 wire wraps per inch. And that gives you a max resolution of 0.0005 inches. Most of them, like we said, kind of top out around 0.05. We have the question here, is there a better solution? And there is. If that stepwise output is a big concern to you using something like this where you have conductive plastic. So it's a carbon impregnated plastic that's conductive. They eliminate that stepwise output. So that improves resolution. Essentially it turns it from that discrete step-by-step thing to a continuous response. But you introduce other types of errors, and it's more expensive. So it has its downsides. One of those other errors comes from it's part of the carbon impregnated plastics characteristics. It's just that you get a 0.2 to 0.02% linearity error with that. Put this slide on here to compare the two different types. Over here we have the wire wound, and over here we have the conductive plastic. You can see they cover fairly close to the same range, but the conductive plastic one is more expensive, more than 50% more expensive. The resolution error is 0.26%. Over here, essentially, there is no resolution error. The linearity error is only 1% over here, but it's plus or minus 2% over here. And then this one has a much more finite life. This one will last for 5 million turns, while this one will only last for 100,000. I briefly mentioned touch screens, and most of your smartphones and most modern devices now are capacitive, but some of the older and less expensive ones, probably the ones that don't work as well, maybe the ones where you're checking out at the grocery store, they might be the membrane potentiometer type. So essentially it's a 2D potentiometer. It provides X and Y coordinates based on where you're pressing down and works on that modification of the resistance principle. So wondering where I was, oh, here. This is where we're going to do the example. Okay, so this angular or rotary potentiometer, it can measure a max angular displacement of 270 degrees It has a resistance range of 0 to 500 ohms. Input voltage equals 15 volts. And the output is connected to a 5 kilo ohm load. So this would be that high input impedance that we said is needed for this and is problematic. And the question is, what is the output at 45 degrees displacement. It could be helpful here to start out with a figure. So let's go from about here. So this is gonna be our output voltage. And this is going to be our source voltage. And we have that 5 kilo ohm load here. So the wire wrappings, the resistance of this angular potentiometer, they're going to go around like that. And we're going to have our slider out there at some angle of displacement. So this we're going to call R1, and this side of it we're going to call R2. I mean, that's physically the layout of that circuit. It might help our engineering, more rectilinear brains to draw it out more like this. So we have, this is more like that variable voltage divider. So you have R1 up here. We have R2 down there. So this is where we connect our source voltage, and this is the total displacement possible. And this is our slider position. So this down here is R2, and this is our displacement. And then we have our 5 kilo ohm load, and we have our output voltage there. So that might be easier to comprehend. Now we know that R1 plus R2 is 500 ohms. And we know that our displacement is, that we're after, is 45 degrees, and the total displacement is 270. So we can find R2 by setting up a little ratio like this. So R2 over 500 ohms. So this over 500 is equal to 45 degrees over 270 degrees. Therefore, our R2 is 83.3 ohms. And since R1 plus R2 is 500, our R1 is going to be equal to 500 minus R2, which is 416.7 ohms. And then without this load in here, that would be the equation that we gave for a voltage divider. The first big red box of today's lecture. So that is, let's just write that down as a starting point. Without the load, we have an output voltage is equal to the source voltage times R2 over R1 plus R2. now we need to consider that load. So with the load, R2 is parallel with that 5 kilo ohm load. Let's go to the other page. Therefore, because they are parallel, we want to add them together in parallel. So let's call that just R sigma. So it's going to be just equal to 1 over R2 plus 1 over 5 kilo ohms. Just adding resistors in parallel. So our sigma is going to be equal to 1 over 83.3 ohms plus 1 over 5 kilo ohms, and that is 81.9 ohms. So we substitute that in for R2 then. That's the last step. So our output voltage is going to be equal to the source voltage times R sigma over R1 plus R sigma, which is 2.46 volts. Then let's note it would have been 2.5 volts without the load. So 0.04 volts error. If we have time, we'll come back and do another example like that. It kind of explores that a little bit more. But first, let's move on to LVDTs, or variable differential transformers. There's the linear type and the rotary type. So LVDT is linear, RVDT is rotary. And this is what we're going to be doing in lab next week. Okay, the premise of these are you have an AC magnetic field is produced by a primary coil. So here we see, we have a section through one of these. Actually, it might help to go ahead. This is what one looks like. So you have this core, or let's say you have this rod that's connected to a core, and that makes contact with whatever is displacing. So that moves this core. And what we're seeing here is a section through that. So back to what the premise of it is, we have this AC magnetic field produced by a primary coil. So there's a primary coil here, a bunch of wire wrappings. We apply an AC signal to it, and that creates a magnetic field around it. And when this rod, whenever what moves translates its motion to the core through this rod, when that moves that core, that displaces the spatial distribution of that magnetic field. So if it's in here and it pushes it this way, then that magnetic field is going to get pushed over towards secondary coil B. If it moves this way it's going to get moved over towards secondary coil C. So that AC magnetic field then induces a voltage in these two secondary coils. Depending on which direction it's displaced in, it's going to produce a stronger AC voltage in that coil. And we're going to see a circuit here about how these are combined together to get us our output. But we're starting to dig into that now. So it says two secondary coils are in series and 180 degrees out of phase. So I think we're going to see that. Well, so here we're just seeing that section again. But here is the circuit. So you apply your AC voltage. We're just going to do that with a function generator. So we apply an oscillating sinusoidal signal to it. Coil A, it produces that magnetic field. Depending on where the core is, it displaces that magnetic field either towards coil B or coil C. Here in this case, it's closer to coil C, so we're going to have a lot stronger signal here in coil C than we do up here in coil B. And if you see the way that they've flipped this here, this combines them 180 degrees out of phase. So they're in series, right, one after the other, but they're flipped relative to each other. So 180 degrees out of phase, that's your output here. It's probably just saying more what we just said. So secondary coil voltages oppose each other. They're out of phase. If it's right in the middle, they're going to be exactly the same size and they're going to cancel. So there's no signal. Then if you move to one side or the other, you're going to start to get a signal out. So you get induced voltages in secondary coils, which are affected by the magnetic core position. Like I just said, if the core is centered, the induced voltage in the secondary coils are equal and opposite. They cancel. If the core is closer to a coil, induced voltage in that coil will be higher. That'll dictate the output. So here we see, so this signal here is our primary coil. This is our input. We're creating the magnetic field with this. And so core is displaced upwards from the center. So it's up here. So coil B is getting more signal induced in it from the magnetic field. So we see coil B is a greater magnitude than coil C. And here they are, we see they're 180 degrees out of phase, right? Here we're going up, while here we're going down. So the output, since we add those together in series, is going to be the interference of these two. So destructive interference, right? This coil B is canceled out by coil C. So coil B minus coil C gives us this dark line as our output. And if we displace it in the other direction, more towards coil C, the output still stays the same, but now coil C is higher magnitude than coil B, and they have destructive interference resulting in this output that's closer to the phase. It's in the same phase as C, but reduced in magnitude by whatever we're getting from B. So this is the output, and so AC root mean squared output. So the output voltage is AC RMS and always positive. Right? By RMS, that's what we're doing. We're making it always positive. So for both directions of displacement. So this is what that output's going to look like. If you displace in one direction from center, you're going to get this. If you displace from the other direction, you're going to get this. So just looking at this, it doesn't give you any idea of the direction, right? If you're on this side, you're going to get, say, it's 5. If you're on this side, you're going to get 5, X or whatever we want to make up some value. So it gives no obvious information about direction core was displaced. we do solve this with signal conditioning. It comes back to the phase, right? If we can determine the phase, then we can determine what direction it's in. But just in this AC RMS output, we can't understand what direction it is. But there is important stuff here. So the voltage versus displacement is linear up to a certain point. So within this range, the output is linear. Essentially, that's the useful range. If you go outside of this, it levels off, and there's you don't get any change. You don't for a change in displacement. That's useless to you. So it becomes quite nonlinear, and then no useful info. So practical LVDTs operate in the linear range. Then here we have this statement down here that sensitivity is determined from slope. So that's an important thing. You're going to need to determine that in lab. There are actually two sensitivities that we are interested in. Remember, sensitivity is the change in output for the change in input, so that's the slope. The first way that you need to do it in lab is just simply that change in output per the change in displacement. Just simply the slope. So that's S1. And this whole S1 and S2 thing is a fairly common thing among measurement systems. So S1 is what we're familiar with. The S2, the difference there is that you divide, basically you're taking the input voltage out of it. Right? Here we're dividing that input voltage out of the sensitivity. And so say you have your LVDT set up in something and you apply a source voltage to it. You're interested in what output voltage do I get per the displacement with whatever input voltage you set it up for. But say you're trying to compare your LVDT to one of the other groups who might have had a different input voltage. So by dividing the input voltage out of it, taking that input voltage out of it, you make it more that you can compare one device to another device independent of what somebody set the input voltage to. So you need to graph the output. So that's one thing. You need to determine those two sensitivities. And another thing is the lab requires students to graph the output using a single equation. And the simple relationship of y equals mx plus b will not work, right? Because it's V-shaped. So how do you think you get around that? Yeah, absolute value. So must be modified to the form y equals m, absolute value of x plus b. The other thing that you're going to need to determine in lab, like we said, the phase angle is how we get the direction information out of it. So we need to be able to determine the phase angle. So first, let's just read this text up here. It says, calculating phase angle between input and output voltage. Input and output are magnetically coupled. Therefore, the frequency must be the same. However, the input and output may be out of phase. Right, so they're same frequency, different phase. So how do we determine that phase angle? The equation, some of this, I suppose, is a little bit backwards. This phase angle here is what we're after. So phase angle divided by 360 is going to be equal to the change in time divided by the period over here. So change in time is just, if we take the same point in the waveform, how long does it take until we get to that same point in the other waveform? And then the period is the inverse of the frequency. So if we go back to this second statement up here, that if the input and output are magnetically coupled, the frequency must be the same. So whatever you put in for the frequency from your function generator going into this as your source voltage, you take the inverse of that and you get the period. Then you divide the change in time between the two different waves by that period. That is equal to your phase angle divided by 360. Now, you're going to be using an oscilloscope for this lab. Part of this lab is just becoming familiar with an oscilloscope, more familiar. You probably used one in circuits. Fortunately, we have some really nice new oscilloscopes in lab now. But there are a couple different ways of measuring it. You can, so there's a cursor function. You can set a cursor here and then set the other cursor here, and it will tell you the change in time between them. Or you can do some more of the, like, press some more buttons to get in where it can just automatically tell you the phase angle. So you can do that route if you want to. Either one of those is fine. So that's what this last thing says. Phase angle measurement features built into the scopes. You can do it more manually with the cursors and this equation, or you can just press the right buttons to get the phase angle measurement function. Okay, here we're talking about different, we're still on the LVDTs, but there are different types of LVDTs. So first there's the AC LVDT, which is what we've been talking about. So it's external circuitry, very robust, shock resistant, waterproof. So very durable, simple, so very robust. You do need a function generator, right? You need to give this AC source voltage to it. That might be difficult, say if you're out in the field. So there are DC LVDTs, which have a lot of that circuitry integrated into them. So like the DC LVDT, you could hook up to a battery in the field, and then it has an integrated oscillator, an amplifier, and a demodulator. So it makes it a little less durable, more complicated, more expensive, but some cases that might be the perfect application. So demodulator, I put in a little definition down here for you if you're not that familiar with it. But a demodulator recovers info content from modulated carrier wave. There are many different configurations. So there's the gauge head and there's spring loaded. We're trying to get new, like when you get into lab and you see these test specimens with LVDTs mounted in them, you can tell they're quite old. That part, we're having the shop make us some new ones. I kind of doubt they're going to be ready for this semester's lab. You do get the new oscilloscopes, but you're going to have to kind of deal with these older test specimens. The newer ones, so the older ones are just this basic version that we've been talking about, and that little rod is physically, mechanically coupled to what is, how we're controlling the displacement. The newer ones are going to be spring-loaded. So mostly I'm just telling you they're different types. Now, moving on to the rotary variable differential transformers. The core concept is the same thing. You still, right here you have this primary AC voltage being applied to it. You have a coil. It's producing a magnetic field. The main difference is just this core, right? So now you have an input shaft that, here we're seeing a section through this. So the input, that rotary motion, is going to displace the core like this. So it's either going to go, in this case, it's closer to coil B, so it's sending the magnetic field up here. If it rotated out of the page and down, in this view, this would rotate this way, and it would shift the magnetic field to coil C. Here, more of that signal is being induced into coil B and less in the coil C. And from here on out, it's the same thing. In series, out of phase. This is kind of like this view, but maybe a little bit less schematic. It's more like the actual thing. You have your primary coil right here, and you have your secondary coil here, and your other secondary coil here. So you measure angular displacements. Output voltage is linear over a range of up to plus or minus 40 degrees. So this here is probably plus 40, could go to 0, and then down to negative 40. So the advantages of LVDTs are you have minimal wear and contamination because there's no surface contact like there was with the potentiometers. They work the same in both directions, so there's negligible hysteresis. They have very good resolution. So remember the potentiometers, most of them were topping out around 0.05. If you want to get the highest quality, most expensive ones, then you could go out to 0.00005. With an LVDT, you're out to 0.000001 inch. So a thousandth of a mil. So quick response time, just limited by the rise time of the amplifier. And you can have ranges from millimeters to tens of centimeters. They can be small, and there's no damage if they're out of range. You just pop the core back in. So lots of advantages. The disadvantages are they're not good for large displacements. It must be roughly 3 times the measurement range. Right? It has to do with the coils. 3 coils, you gotta have space for them. Direct contact is required. That core has to touch something, and that core has some mass to it, so the inertia of the core limits the dynamics. It's going to give some loading error. And the dynamic measurement is limited to 1/10 of the excitation frequency. This isn't the same thing as the Nyquist. Like Nyquist would be a separate thing that could affect this. But this has more to do with, you have an AC signal, and if your oscillations are close to the oscillations of your signal, then that's going to confuse the system. So if you limit your oscillations to 1/10 of your excitation frequency, you don't have any problem with that. And it requires signal conditioning. That's to get the directional information. So a little bit more about that signal conditioning. So by using phase information, we can determine the sign of the displacement. So if you here measure that the output is in phase with the input, then you know, say you're on this side. And here, if you measure that it's out of phase with the displacement, then you know you're on this side. So using that information, you can say, okay, instead of this, we're going to make it this. So you get that directional information. We know if we go this way, we're at +5. If we go this way, we're at -5. And this is kind of idealized here. Like it's showing your output is perfectly in phase with your input. You're going to see small shifts even in that, because you're going to take your output of the function generator and you're going to split it. And part of that you're bringing in to the oscilloscope. And then you're taking the output after the Lvdt into the second channel. And you're looking at the difference between the two of those. And even if you're in phase, that where you split the signal and ran that directly into the oscilloscope, that's a shorter path than the path that goes through the Lvdt. There's a resistor there. So that path, a little bit longer, you're going to see a little bit of a phase shift even between the one that's in phase and your input. And then, so that varies, you know, depending, there's like 2 different load resistances that you look at. I can't remember which, but one of them is, I think just because of the circuitry within that decade box is a little bit longer. But you might see anything from, say, like 3 degrees to 30 degrees. And then when you switch over to the other side of the displacement, so it's out of phase, you should see that, whatever you saw, like that 3 to 30 plus the 180 degrees. So there's a little bit of a shift between the primary and the output that's in phase with it. This is kind of idealized here. But you're more interested in We're going to ask you to measure all of those just to be aware of them, but you're more interested in that 180 degrees shift. So a little bit more about the signal conditioning. So we just have this kind of like flow chart, this schematic diagram here. So we have our power supply, we have our frequency signal generator. This is that split I was talking about. So you split it, you take a reference signal, and then you bring this into, in our case, the oscilloscope. And then that other output from the frequency signal generator, that is what goes into the Lvdt sensor. And you get an output there. So by comparing this reference signal to the output signal in our oscilloscope or whatever signal conditioner you might be using, that's where we determine the sign of the displacement. Here we have a cut sheet for an Lvdt. So this is a DC Lvdt. Pointed out a little bit of linearity error, pretty small amount. So FSO, so less than 0.2% of the full scale output. That might be one of the most important things on here. Okay, which coil has a higher voltage? C, right? You know what, we have 5 minutes left, but I don't know that we would be, I think we would not make it completely through this example. I think it would be kind of rushed at the end. The end of it is actually the important part, so I don't know that I really want to try to squeeze that in right now. I think we should probably just end it here, and we'll start with that example on Thursday. So have a good day.